we'll be presenting our research on brain tumor detection with QNN and NMR algorithms. So first, a quick overview of brain tumors. Brain tumors are the uncontrollable growth of cells that form an abnormal mass of tissue in the brain. They make up about 85 to 90% of all primary central nervous system tumors. Currently, about 1 million Americans alone live with a primary brain tumor. Of these, there are many types of brain tumors. Some of the main ones include glioma, meningioma, or pituitary tumors. Specifically, they can also be classified as benign or malignant. About 28% of tumors are malignant, meaning they can be cancerous and life-threatening. In 2023, 26,940 people are projected to be diagnosed with a malignant brain tumor. And regardless of whether the tumor is benign or malignant, they can still be harmful. So, as a tumor in the brain grows, it can apply pressure on the skull or other parts of the brain, block fluids in the brain, and even cause bleeding. Aside from being life-threatening in certain cases, brain tumors also cause symptoms such as difficulty balancing, loss of vision, or memory issues. So, accurate and early detection of brain tumors is crucial for doctors to determine treatment methods for patients. Um, in terms in terms of detection, currently the most widely used technique is in the medical field is magnetic resonance imaging or MRI scans, which produce detailed images and are then examined manually by radiologists. This poses several issues. For example, it creates a heavy reliance on the experience of the radiologist and can be prone to error, especially with the complexities such as the size, location, and other abnormal features that come with brain tumors. Specifically, early stage tumors, which can be difficult to spot, are particularly prone to error with manual detection. And as the number of patients increase, the amount of data has also been increasing, making manual brain tumor detection more costly and inefficient. Our solution is to create an algorithm that would be more accessible and solve some of these issues. In an attempt to improve accuracy and speed, there have been many recent developments in the field in researching deep learning approaches, specifically with CNN algorithms as an alternative to manual methods of brain tumor detection, and these approaches seem to have been largely successful. This leads to the basis of our research, which is to find whether the MMR and QNN algorithms, which we'll discuss further, can outperform CNN algorithms. So the next part is the QNN algorithm. Um, the skull stripped image from the initial MMR processing acts as an input for the QCNN or quantum convolutional neural network. Um, we at our stage in research, we finished the QNN algorithm and we're testing it now. So Um, so for the skull stripping, it isolates the brain by removing the skull and noise, and we used erosion and dilation to create balanced edges and gaps, and the contours found are smoothed to identify the brain tumor, and then the mask is applied to the original MRI for the skull strip brain image, and this is just one part of our pre-processing algorithm. These are the top images are the original MRIs, and then the bottom images are the skull stripped versions. So the mathematical morphological reconstruction algorithm is another part of our pre-processing steps. It enhances and extracts image structures by iteratively combining dilation and erosion operations. It removes the noise and artifacts from the images and segments the MRI to find regions of interest with probable tumor. The process is to split into similar images and different images. So the um, first, the first step in the MMR is to make the marker and the mask creation, and then the second is to perform noise removal, and then watershed thresholding, and then lastly segmentation. So these are the results of the MMR. It highlighted possible regions that could have a tumor. So the next part is the QNN algorithm. Our QNN will be, oh, it stopped screen sharing. So our QNN will be using a convolutional neural network for the architecture, and we'll briefly go over what a classical CNN looks like. The CNN is a deep learning algorithm that is fed training data and detects pattern to process images and classify those images. The algorithm is able to learn the relationship between certain features in the image and then label those images accordingly. Typically, we'll have an input layer, hidden layers, and an output layer. For example, here there are two hidden layers, um, but you can have more or decide how many you want. In this image, these circles are perceptrons, which takes an input and gives an output. In the hidden layers, functions are applied to the inputs with certain weights and parameters. The algorithm, what it does when it's learning is it adjusts these weights to detect patterns. To take a closer look at the hidden layers, in our case, we are primarily looking at convolutional and pooling layers. The convolutional layer performs feature extraction, and the pooling layer reduces the dimensionality, meaning it reduces the size of the image. Finally, the last stage is the output, which classifies the image. So our QNN, our quantum neural network, will be using classical data with quantum computing. With our quantum convolutional neural network, we will be using a combination of quantum computing concepts with the CNN we just discussed. Like the classical CNN, we'll have convolutional and pooling layers, but we'll also be using qubits and quantum circuits. As you can see in this image, we plan to apply alternating convolutional and pooling layers on our quantum circuit. And the purpose of our research is to test if the QCNN with a quantum computing aspect has better accuracy or speed than the classical CNN. So specifically, the QCNN algorithm will contain three main parts: the encoding, processing, and measuring of the data. In the encoding step, the classical input data is converted to a quantum circuit through methods such as angle encoding. This will put the qubit into superposition and apply rotation so that the data can be further processed. Next is the processing step. This is like the hidden layers we just talked about with the classical CNN. This step would include applying gates and entanglement with certain parameters. Specifically, like the classical CNN will have a convolutional layer and a pooling layer in the algorithm. The convolutional layer would involve the same feature extractions that we discussed previously, and the pooling layer would reduce the dimension of the quantum circuit while keeping the same data. How it does this is essentially we encode the information from one qubit to the other qubit. Once we do that, we can disregard the original qubit for the rest of the process. So if you take a look at the image here, the data from Q0 is encoded into Q2, and then the data from Q1 is encoded into Q3. So at the end, we're able to disregard Q0 and Q1, and we're left with Q2 and Q3. So this pooling would reduce the number of qubits in our circuit, in this case from 4 qubits to just dealing with 2 qubits, and we would just repeatedly apply this pooling layer until we have 1 qubit. Eventually, the last step is to measure the output of the single qubit, and when we measure it, the output will be in the form of a probability of a certain state, which would then be translated to what that would mean classically, so depending whether or not there will be a brain tumor. For future work, we need to complete the testing of the QCNN. Then we'll compare these results to the regular CNN algorithm and and see if there's any noticeable advantage in terms of speed or accuracy. And future possibilities to expand this project down the line would be to classify types of tumors rather than simply detecting them, which would help doctors determine whether this tumor is malignant or not, and what kinds of treatments would be useful or necessary, and help with different factors that would come into play depending on the type of tumor. So we'd like to thank our advisor, Dr. McMahon, for helping us throughout this project, and ASDRP for the opportunity to conduct this research, and of course the rest of the researchers on our team who contributed throughout this researchers. Thank you.